How's it going, Accelerated Chemistry students? This is Mr. Spurk, and this is your Chapter 18, Section 2 notes on the progress of chemical reactions. Today's lesson is very math heavy, so make sure that you pay extra attention and you're writing down the practice problems as I work through them, and we're going to use these skills in class tomorrow. So we're going to first start by talking about rate laws. Let's suppose there were a reaction with the only one reactant and one product. So A to B. The rate at which A forms B can be expressed as the change in A, or delta A, with time. So the rate equals delta A over delta T. Try to relate this to things like miles per hour. It would be like how many miles you've traveled, or the change in miles over the change in time. The rate of disappearance of A, or A to B, is proportional to the concentration of A. The proportionality can be expressed as the concentration of A, or a bracketed A. Brackets around an element or a compound means concentration, multiplied by a constant K. So the rate equals K times the concentration of A. This equation is a rate law, an expression for the rate of a reaction in terms of the concentration of the reactants. The specific rate constant, K, for a reaction is a proportionality constant relating the concentrations of reactants to the rate of the reaction. The value of the specific rate constant, K, in a rate law is large if the products form quickly. The value is small if the products form slowly. The order of a reaction is the power to which the concentration of a reactant must be raised to match the experimental data on concentration and rate. In a first-order reaction, the rate is directly proportional to the concentration of only one reactant. So what that means is that the concentration of one reactant has a huge effect on the rate of the reaction. So over time, the rate of reaction decreases because the concentration of the reactant is decreasing. So when there's less of the reactant, the rate of the reaction is going to slow down. The reaction from A to B is a first-order reaction. If the concentration of A is reduced by 1/2, the reaction rate is reduced by half. The rate, or delta A over delta T, at any point on the graph equals the slope of the tangent to the curve at that point. And a tangent line is just those red lines that we can see here. And a tangent line just touches our main curve at one point, or an instantaneous rate. There are higher order reactions, so in some reactions, two substances react to produce products, and we've seen this many times. In the general reaction for a double replacement reaction below, the coefficients are represented by the lowercase letters. And this is something that we've looked at many times. For the reaction of A with B, the rate of reaction is dependent on the concentrations of both A and B. So the rate here is equal to the rate constant, K, times the concentration of A raised to a power x times the concentration of B raised to a power y. When each exponent in the rate law equals 1, so that would be when x and y are both 1, the reaction is said to be first order in A and first order in B. The overall order of reaction is the sum of the exponents for the individual reactants. So a reaction that is first order in A and first order in B is then second order overall. So 1 plus 1 is 2. So the overall order of this reaction would be second order. The actual order of a reaction must be determined by the experiment. So we can predict it, but then we can experimentally determine what order this reaction is. So now we're going to find the order of a reaction from experimental data. So consider the reaction A to B. The rate law for this reaction is the rate equals K times the concentration of A raised to the power x. From the data table in the From the data in the table, find the order of the reaction with respect to A and the overall order of the reaction. So what we did here was we did this reaction 3 times. You can see there are 3 trials, and we just ran the reaction from A to B. In the first trial, the concentration of A is 0.050 molar, and the rate of that reaction is 3.0 times 10 to the negative 4 molar seconds. In trial 2, the concentration of A was 0.1, and in trial 3, the concentration was 0.2. And as you can see, the rate increases as the concentration increases. So now we're going to switch over to our math brains, and we're going to figure out the order of this reaction. So the first thing we're going to do is we're going to compare 2 of these trials. So I'm going to start by writing rate 2 over rate 1. And we know that the rate law for each of these is K times the concentration of A. And since this is for rate 2, it's going to be the concentration from 2 raised to the x power. And we're dividing that by the rate law for rate 1. So that's going to be K times A1 to the x power. So we can do some algebra properties here, and we can cancel out the k's. And then we are going to move our exponent to the outside. Since these are both concentrations are raised to the same power, we can rewrite this as the concentration of A2 divided by the concentration of A1 raised to the x power. So now we have our equation, and we can just plug in our values. So rate 2 from the table is 12 times 10 to the negative 4 mole per liter seconds. Rate 1 is 3.0 times 10 to the negative 4 mole per liter seconds. We also know the concentrations of each. So the concentration from reaction 2 is 0.10 molar. And from reaction 1, it's 0.050 molar. All raised to the x power. Now you may be thinking, why did I put rate 2 on top and rate 1 on the bottom? It really doesn't matter which one you choose, because algebraically you're still going to solve for x. However, I chose to put rate 2 on the top because the numbers are bigger. Rate 2 is 12 mole per liter second, and rate 1 is 3 times 10 to the negative 4 mole per liter second. So when I divide those out, I'm going to get whole numbers rather than decimals. And it works out the same way for the concentrations. So you can do either way, but I just chose to put rate 2 on top and rate 1 on the bottom. So now we're going to start doing some math. When we divide 12 times 10 to the negative 4 by 3 times 10 to the negative 4, we get 4.0. And those units are going to cancel out. When we divide by the same unit, they cancel. So it's just 4.0 equals 2.0 raised to the x. So if you have never done this in algebra before, we can bring down this exponent of x. And we're going to introduce what's called the natural log. And it is just the ln button on your calculator. When I took math, I grew up calling it just the ln, just for ln. So if we take the ln, or the natural log, of 4.0, and we take the ln of 2.0, it brings down that exponent. So now it's the ln of 2 times x. So now we can just divide both sides by the natural log of 2. So we have the ln of 4.0 divided by the ln of 2.0 equals x. And we can punch this into our calculator, and we get 2.0. Now you can't just divide 4 divided by 2 because the natural log does do some funky things to our numbers. So if we had different numbers, we would make sure that we punch in ln of 4 divided by ln of 2. And so we get 2.0. So what this means is that the reaction is second order. And what that means is that rate 2 is 4 times greater than rate 1. So I know that is a lot of math. It seems very confusing, but this will become useful for us as we move forward. So this is a lot of algebraic rearrangements and moving things around. I want to work through another problem because I know that this is tricky. So this problem tells us that the reaction order is second order. If the initial concentration of A is 2.0 molar and the initial rate is 9.6 times 10 to the negative 7th mole per liter second, what is the concentration when the rate is 1.2 times 10 to the negative 7th mole per liter seconds? So basically we're going to set this up the same way, and we are going to just end up solving for a different variable. So we still have, if you remember from the last problem, rate 2 again. I'm just choosing to put rate 2 on top just because this is going to be easier for us in the long run. So rate 2 divided by rate 1, and that equals the concentration of A2 divided by the concentration of A1 raised to the x. So when we start plugging in values we know that the rate 2 is 1.2 times 10 to the negative 7th mole per liter times seconds divided by 9.6 times 10 to the negative 7th mole per liter times second. And when we start plugging in the concentrations, we do not know the concentration from the second reaction. That's what they're asking for. What is the concentration when the rate is this? So we're looking for that value. We know that the concentration from the first reaction is 2 molar. And we know that our exponent here is going to be 2 because it is second order. So now we just start doing some algebra, solving some values. So 1.2 to the negative 7th divided by 9.6 times 10 to the negative 7th is 0.125. And again, those units are going to cancel. And now here on the right side, we have the concentration of A2 squared divided by 4.0 molar squared. I just distributed the power of 2. And again, if you're a little rusty on your algebra, or if you haven't seen something like this, we will talk about it in class tomorrow. So as we go through, we're going to multiply this through to the other side. So 4 times 0.125 is 0.5 molar squared, because remember we had to square the 2 and the unit, so it is molar squared. And that is equal to the concentration of A2 squared. Well, we don't want the concentration of A squared, we just want the concentration of A. So we can take the square root of both sides, because whatever we do to one side, we have to do to the other. So we end up with 0.71 molar, and that is the concentration of A in the second reaction. So again, I know this seems like a lot of math, but we will work through it and we will nail this down. All right, so we still need to talk about one-step and multi-step reactions. So an elementary reaction is a reaction in which reactants are converted to products in a single step. This type of reaction has only one activation energy peak and one activated complex. Most chemical reactions consist of 2 or more elementary reactions. The series of elementary reactions or steps that take place during the course of a complex reaction is called a reaction mechanism. An intermediate is a product of one step in a reaction mechanism and a reactant in the next step. An intermediate has a more stable structure and longer lifetime than an activated complex. Intermediates do not appear in the overall chemical equation for a reaction. So think back to when we were looking at Hess's law. We had a goal equation in mind, and we were adding together 2, 3, maybe even 4 reactions to get to that goal equation. So that is a multi-step reaction. So that's what we're looking at here. When we were adding those reactions together and we were crossing things out, those are our intermediates. They appear as a product in one reaction and end up disappearing in another reaction. This figure over here shows a reaction progress curve for a complex chemical reaction. A reaction progress curve shows all the energy changes that occur as reactants are converted to products. The graph has a peak for each activated complex and a valley for each intermediate. So this looks like 1, 2, 3, 4 different reactions to get to the product, the desired products. In a multi-step chemical reaction, the steps do not all progress at the same rate. It's kind of like running on a cross-country team maybe. Not everybody runs at the same speed, but you need everybody to finish to reach that final goal. One step will be slower than the others and will limit or determine the rate of the overall reaction. So when we look at this equation, we see that nitrous oxide is decomposing into N2 and O gas. The O is the intermediate. For the decomposition of nitrous oxide, the first step is the rate determining step. To increase the rate of the overall reaction, you would need to increase the rate of the first step. So you can see that O gas is formed here, and then it is consumed here. So this is our intermediate. It does not appear in our final reaction. All right, so we finally made it through. In review, the value of the specific rate constant K in a rate law is large if the products form quickly, and the value is small if the products form slowly. Most chemical reactions consist of 2 or more elementary reactions. And here are some equations that we looked at. Rate is equal to the change in A per unit of time. And that's also equal to a constant times the concentration of A. And the rate law for a second order reaction, rate equals K times the concentration of A raised to the X power times the concentration of B raised to the Y power. So we did it. We finally made it through. As always, all the information on these slides has been acquired and adapted from Pearson Chemistry, 2012 edition of the textbook, the resources CD, and pearsonchemistry.com. Have a great rest of your day.